All right, so today we're gonna start a new section, and we're gonna be discussing basically a select gauge theory, non-perturbative gauge theory phenomena. So in particular, I was originally my plan was to do solitons and instantons, but then I realized that there are more basic non-perturbative stuff that we haven't really discussed. So today we're gonna start the discussion. We haven't done a good job of. We're gonna discuss the magnetic monopole, the Dirac quantization condition, because this is an important one. Then we're gonna discuss theta term, right? Theta angle in abelian gauge theories, right? We're gonna discuss that, where I'm gonna give an example of topological insulators, just something that is like used in physics all the time. And then the next lecture is going to be about the connection of theta term and instantons, right? And then hopefully there will be 3 more lectures left, which is going to be all large. But this is all from now until the end of the semester, we're going to be working on various non-perturbative aspects of gauge theories. As we saw, these are examples where there are lots of interesting sensible theories, strong, actually interacting theories are among gauge theories. I also wanted to have to discuss 2D gauge theory. I might do that at some point. I even have the slides and lecture ready, but we'll see how much time we'll have. Do you guys know what is special? Like, do you have a one-liner for what's special about 2D gauge theory? Say QED, the U1 gauge theory in 2D. Let me ask it this way. How many degrees of freedom did photon have? Sorry? In D dimensions. D minus 2. There were D, there was the A0 that we solved because it's decoupled, and then there was the gauge transverse condition. So what does that say about 1 plus 1 D QD? There are no propagating degrees of freedom. The theory is topological. That's why it's a prime example for the study of like non-perturbative aspects. The theory is very simple. All right, that's just one thing to do. Okay, so I'm gonna, as usual, start by a review of the previous lecture, and there will be a sharp transition from the CFD stuff to the new stuff. So previous lecture, we discussed operator product expansion and conformal field theory. Recall that the conformal transformation is a diffeomorphism x mu going to x prime mu, such that changes the metric by an overall function that's x dependent. We saw that in general dimensions, like these, in particular d larger than 2. By d I mean space time. The generators are the transformations are translations, rotations. Let's say I'm discussing Euclidean conformal group. So translation and rotations. This is the Euclidean Poincare. This is the Euclidean Poincare, because rotations are Euclidean Lorentz transformations. There is the extra new stuff are dilatations or dilations and special conformal transformations. Or another way of thinking about it is dilations and inversion. Because inversion, translation, inversion is special conformal transformation. Under special conformal transformation, the metric changes by this much, by this function. What other transformation here changes the metric? Dilations, right? The rest of them are symmetries. Isometries, which means that they leave symmetries. They leave the metric invariant. We said that the conformal nodal charges in R d minus 1 comma 1 or the Lie algebra is OD comma 1 is basically the Poincare group. This is the Poincare group. These are the generators, the Lorentz group, and this is the translations and Lorentz generators. And then there is a new generator, which is a special conformal transformation that satisfies the following relations with Lorentz transformations. Let's look at scaling. Scaling in P mu give you I P mu. Scaling in K mu gives you minus I K mu. These look like the raising and lowering operators. And similarly, these guys look like raising and lowering operators. This is we discussed very briefly the representation theory of Lie algebras, and we said that what we do is we take the carton, this maximal abelian Lie algebras, subalgebras. We diagonalize in that basis, and you're going to have a bunch of raising and lowering operators labeled by this extra label. So here, what we diagonalize is in the basis. We diagonalize in the basis of L mu nu, which is what's the quantum number for that? Spin. And we diagonalize in the basis of D, the quantum number for which is scaling dimension. Then P mu and K mu, they act as raising and lowering operators. And then their commutator, of course, should be written in terms of the diagonal object. All right. So because we're diagonalizing everything in the scaling and Lorentz Lorentz generators basis, let's just for a second focus on spin zero for simplicity, to simplify our analysis. So we're looking at scalar operators, and we're looking at scalar operators that are the eigen operators of dilations, right? Meaning that the commutator of the operator with dilation is just delta, right? So of course, if you find, we're going to call those operators, what do I want to call it? I want to call them well, let's call them scaling operators. If you take one such operator, act with P mu, the Lie algebra we just described, right? Raising, when you say P mu is like raising, it means that this is a new eigenoperator with the new eigenvalue that's delta plus 1 and delta minus 1. So it's corresponding lower 1. Now, as is usual in representation theory, we often in physics, we look at the lowest weight representation. That is the guy that is basically killed by K mu, right? So this we're going to call a conformal primary. It's a simultaneous eigenoperator of scaling and L mu nu, right? That is killed by K mu. This is the lowest weight. Once you find that, you act with P mu and you create the descendants, right? So these descendants are algebraically built from the primary. If I want to describe to you the theory, all I have to do is, well, the spectrum of the theories, that which means that the spectrum of the quantum numbers corresponding to D and L mu nu, I have to tell you the scaling dimension. I'll have to give you a list of scaling dimension and spin of primary operators, conformal primaries, right? Because then the rest, you know how to construct all the other operators, right? So P mu will raise well, in this case, will increase the spin by 1. Yeah.
Are there any constraints in the values that the scaling dimension can take?
Of course, yes. Where do those constraints, where would they come from?
Is it just like how we get it for like SU2, for example?
Yeah, no, I understand. Where would they come from? So this is the data that's supposed to describe a conformal field theory, right? We listed the axioms, right? If the list of numbers that you give will check all the axioms, it will be a legitimate theory, right? So where does it come from? It comes from all the axioms, in particular crossing, right? It comes from checking the crossing equations that we use. Actually, we use bootstrap to constrain deltas. So an example of such theory that we discussed was massless free complex scalar field. This is the action, Lagrangian density. In this theory, D is larger than 2. So phi 0 is a primary of scaling dimension D minus 2 over 2, right? K mu and phi 0 is 0. It's also spin 0. So this is a scalar conformal primary. the scaling dimension is d minus 2 over 2, and you apply these guys to construct the descendants, right? And this is the dimensionality of the descendants. Now, something interesting that happens in this theory is that del squared of phi is actually 0. That's the equation of motion. And that's the statement in algebraic construction of the theory. That's the statement that this vector is a null vector, right? We said that every time you have a conserved current, like J mu in the case of complex scalar field, which was, do you remember what J mu was in complex scalar field? Number of particles minus antiparticles. Then del mu of J mu is 0, which is a condition like a null state, right? We also said that if you have an operator that has dimension d minus 1 and spin 1, it must be a conserved current, right? We also said that, well, good. We said something else. The more general statement was if you have an operator that's dimension d minus 2 plus s and spin s, it must be a conserved current. What's the other example? Stress transfer, which has dimension d because s is 2, right? That's a conserved current and the conservation laws are there. Okay. Because the algebra is so large, in the discussion of operator product expansion, you could simply restrict yourself to the OPE of the conformal primaries because the rest of them are just algebraically decided in terms of these guys. So operator product expansion will have these functions that depend on the location. I, J, K, A, B, C here are possible Lorentz spin indices, right? In CFDs, we need to consider the correlation function of primaries, right? What are the 1-point functions in a CFD? The 1-point function of primaries in a CFD is 0 unless the primary identity. The 2-point function, you will work it out in your homework, always takes this form. We could use this to diagonalize this form. You could diagonalize by linear transformation of your primaries to bring them in this orthogonal form, orthonormal form, I guess orthogonal form where, yeah, basically this is a 2-point function. Similarly, the 3-point functions of primaries are fixed by the conformal algebra. This is the form of it. These Fijks, they're called the OP coefficients. So if you look at in this expression that we wrote previously, thisCijkabc is basically a piece which is fully fixed by conformal symmetry. It's the function that's fully fixed by the conformal symmetry, and these OP coefficients are basically all that remains. So the conformal data of a CFD is a list of scaling and spin of conformal primaries and their corresponding OP coefficients, right? So I'll have to give you this list. And once you have this list, all that remains is to check the axioms, in particular, associativity of the OPE, operator product expansion. We said that the CFD, the operator product expansion, is convergent. And this means that the knowledge of 2-point function and 3-point function could be used as enough to recursively evaluate to arbitrary precision higher point functions. That's what's neat about the theory. That's why we say that the data is just this function. Good. In particular, we discussed the 4-point function. The 4-point function there are 4 operators inserted. Let's say these are conformal primaries, x1, x2, x3, x4. Using conformal transformations, you could always map 3 of them to fix 3 of them to be your favorite points. Usually 0, 1, and infinity are our favorite choices. And then the last one that remains, we usually represent it on a 2-dimensional space with variable ZZ bar. ZZ bar, if you're wondering what they are, here's U and V. These are conformal cost ratios, and ZZ bar are related this way to U. The very fact that using conformal symmetry, you fix one of them to be 0, the other one 1, and the other one at 3 of them 0, 1, and infinity, it means that you could put 3 of them on a line. Right? Now the 4th one is going to be somewhere. But I can always project that down to a 2-dimensional space, no matter what the ambient space-time is, right? That includes all of these guys. This is precisely that 2-dimensional space. Right? Because the rotation around this line will not do anything. Is that clear? So what are the crossing equations? Well, the crossing equations tell you that if you have 4-point functions like this, you could consider this OPE channel or this OPE channel. So in this OPE channel, because we're looking at the OPE of 1 and 2, F120 is the OPE coefficient that appears. Here, F340 is the OPE coefficient that appears, sum over O. These objects are called conformal blocks, right? They're the contribution of the O operator to the 4-point function of 1, 2, 3, 4. They are functions of the quantum numbers of 1, 2, 3, 4, which are their scaling dimensions and spin, and the quantum numbers of O, right? And ZZ bar. These are known functions. Well, in odd dimensions, they have closed form, and in particular 3 dimensions, they have closed form, and 2 and 4 dimensions, they're known recursively using recursive relations. 2 is a special case, but anyway. And the idea is that by solving these equations, we try to bootstrap these equations to find constraints on the space of conformal data. That's like a huge field of well, there's a lot of research that happened in this area. Any questions?
Assuming the same idea you used to project the 4-point function to a 2D surface can be extended for higher point function like 5, 6. We ever want to consider them? May not be
Some version of it, right? Because higher point, let's say 5-point function, you can always fix 3 of them on a line. Then there are 2 that remain. So you could always use some of the symmetries to bring it down to something lower dimensional, but you won't be able to bring it down to 2.
Yeah, that makes sense.
Yeah.
On like 4 dimensions, it does. Or like we had in 4-point function, we had like 1 degree of freedom to the left, like 1 point to the left, which had like 2 degrees of like ZZ bars.
Yeah. So there are, for example, there are instances if your 4 points align on a line, which is the setup where Z is real, right? These conformal blocks simplify significantly. So people do study these cases, right? Any other questions? So this closes a very short discussion of operator pod expansion. I apologize that we cannot go further in depth into this, but it's a topic that I just want you guys to go and learn about in case you're interested in. But it is a growing or dominant way of it's a growing field. Let's just leave it at that. All right. So for the remainder of the course, we're going to be discussing certain non-perturbative aspects of gauge theories. Today we're going to talk about monopoles and Dirac quantization. So this is like a sharp transition, right? Then we're going to discuss theta term. This was the CP violating term that we call topological in ENM. Then next lecture, we're going to discuss the connection between the role of theta term in quantization and the role of the connection to instantons right? And then the remaining lectures are going to be large and effects engaged series. Is that plan clear? All right. So magnetic monopoles. Let's forget about conformal symmetry, all of that. I think if I teach the course again next year, I will change the order. I'll push the conformal stuff to the end. Like magnetic monopole is an object that emits radial magnetic field, if it exists. So it's something that you put here. Some say it has some magnetic charge G, and here is the B's that go out. So there should already be a little bit of a problem. Well, okay, let me just say a few more words. So the B field, the magnetic field, is this, and of course there is an analog of, there would be, if magnetic monopoles exist, there would be an analog of Coulomb law, right? Which is if you take the flux and integrate the flux over some S2, you're going to get the magnetic charge. So here are two of the Maxwell equations, right? The written in the standard Coulomb gauge, right? Well, actually, no. These are Maxwell equations. The divergence of E is proportional to the electric charge density, time derivatives of the electric field, plus the curl of the magnetic field is the current, electric current. In Maxwell equations, ordinary Maxwell equations, the right-hand side of these two equations were 0. Right? Now, you also hopefully remember that there was a good reason for this term to be 0. You guys remember? It had to do with it was intimately tied to the fact that, so there is no problem with these equations as per se, but if you try to write B as curl of A, right, then you run into some trouble, right? Because the divergence of this curl will tell you that this guy will have to be 0. So already it seems like if you put this magnetic monopole or magnetic charge density, we might have some trouble with the A mu, the gauge field, vector field. But we're going to resolve that issue, right? We're going to see that there are no inconsistencies. We also discussed the duality, if you recall. You guys recall duality in Q1? All right. Dirac quantization. So there is a very interesting consequence to assuming that there exist magnetic monopoles. If there exists a magnetic monopole, well, there is this flux that comes out. Imagine, so you have now two types of charged particles. You have the magnetically charged particles, monopoles, and you have the electrically charged particles. Imagine you have an electrically charged particles and you take this around the loop. As you transport this around the loop, the wave function of this electron or electric charge will pick up a phase, e to the power of I alpha e over h bar. Why does it pick up a phase? This is a Wilson loop, right? With that phase is just a Wilson loop. And that Wilson loop is basically the same as the magnetic flux that goes through this loop. So when you put a magnetic flux, a magnetic monopole here, the phase of this wave function as you go around the loop is changed by e to the power of I g over 4 pi omega e over h bar. This omega is a solid angle. Do you see any problems with this? Sorry? No, that's not a problem here. What you're doing is that you're going around this, and the field operator is picking up a phase. Like, you can think of it as, yeah. Well, okay. The problem is more fundamental. The problem is that you could talk about the flux that goes through the surface, or the flux that goes through the complementary S2 with that disk removed. Now, in that case, this is up to us. The only thing that changes is the direction of the ds, right? That was one was outward facing, the other one was inwards, right? So now, if you pick this direction, this flux, then alpha prime is minus 4 pi. 4 pi is the maximum of the solid angle, minus omega over 4 pi g. So the calculations should match. E to the power of I alpha E over H bar, it has to be equal to E to the power of I alpha prime E over H bar. This instantly tells you that the electric charge times the magnetic charge should be 2 pi n H bar, where n is an integer. Now, this is extremely powerful because it puts the constraints on the electric and magnetic charges of two different particles. We had the electron that was not magnetically charged, it only had electric charge, and we assume we have a monopole, some particle that has no electric charge but some magnetic charge. The magnetic and electric charges should be related. So if I list all my particles that are magnetically and electrically charged, they should satisfy these relations. So there are two options. First, there is charge quantization, meaning that, well, there is the smallest unit of electric charge and smallest unit of magnetic charge, and all the particles carry integer number of those smallest things. This is called charge quantization. Or if you look out there in nature and find a bunch of particles that have irrational electric charges. Remember, the relative charge is a fundamental concept. If it's irrational, it means that there must exist no magnetic monopoles. Quantum mechanics will tell you that that theory cannot have magnetic monopoles. U1 theory. In particular, we could, if we have particles and we have both charges, we often talk about particles that carry both simultaneously electric and magnetic charges. These are called dyons. Electric charge E and magnetic charge G, same particle. So now if you take a dion of electric charge E1G1 and do a loop around a dion of E2G2, they must satisfy these relations. These are quantization conditions. Are these clear? There are very, very strong conditions.
So you have doubts about how you define the, what do you call it, the mu vector? Okay, but I presume you'll like this.
I'll discuss that right next. My next topic. At the moment, I'm just dealing with Maxwell equations, right? I did not remember, this is the whole point. Maxwell equations were Maxwell equations. When we try to write them down, so Maxwell equations are written in terms of E and B and rho and J. These are all physical. There's no gauge invariance here. These are all physical degrees of freedom. Gauge invariance was introduced when we tried to write down these equations as coming from variation of an action that was local. Now, the theory is secretly non-local, but we kind of made it local by introducing this gauge invariance, this bookkeeping thing, right? This is the whole point of it. Right? So now the question is, well, we succeeded in taking QED and writing it as some local action, modulo gauge invariance. Now, if you have magnetic monopoles, can you still do the same thing? And the answer is yes. We're going to see that in a second. Do you have a guess as what the issue is? So when we say that a function and a vector, which is curl of something, cannot have a divergence, we're assuming that that vector field is smooth. smooth vector field, which is careless, something cannot have a divergence. But if it's singular, maybe it's okay. Now, we do know already that when you have electric charge, these electric fields will lead to some singularity at that point. So it shouldn't be surprising that if we allow for fancier singularities in A mu, we could reconcile the two. And that's my next point. But importantly, what we discover is that including magnetic monopoles will force you to insisting on local description comes at the following cost, that not only you have the gauge invariance, the regular gauge invariance transformation, you also have to include gauge invariance transformations for functions that are not single valued, for what are called large gauge transformations. That's the whole point that I wanted to make. So once you have the magnetic monopoles, you're naturally in this world of considering these guys. I'm going to describe it in a second. So as I said, we want to write B, magnetic field, as curl of the gauge vector field. And on the face of it, it looks like we can't arrange for delta, the divergence of B to be zero, non-zero. But that's assuming that A is non-singular. Put G here, right? And here's a suggestion for vector potential. A phi n, right? This is the theta phi r coordinates, right? So theta is this angle, phi is 2 pi around this, r is r. A phi n here is the label for north that will become clear in a second. Is the following function, g over 4 pi, 1 minus cosine theta over sine theta. If you calculate the curl of this guy, you find g over 4 pi r squared r hat. So this looks like the correct gauge vector field that describes a magnetic monopole. Except that there's a catch. Well, you might worry about what happens at theta equals 0 and theta equals pi here, because this is sine of theta. At theta equals 0, this is fine because cosine of this, the numerator has a 0, which is faster. So that's fine. But at theta equals pi, you have a singularity. This singularity is a whole line, right? This is as opposed to the case of when we're talking about charged particles, electric charged particles, when there will be singularity localized at the point. These are the whole line of the singular. Is that clear so far? So this vector potential is just perfectly fine everywhere except for this. Good. Now, let's flip this around. Here is what I'm going to call a vector potential A of S, which is A plus cosine theta over sine theta with a minus sign. You could check that this gives the right magnetic field everywhere at the same as the previous thing, except that it has a singularity here. So it seems like these two choices of vector fields are both describing the physics of interest, so they should be related by a gauge transformation. Interestingly, this gauge transformation is the following. A north of phi is A phi of south plus 1 over r sine theta del phi of omega, where omega is g phi over 2 pi. So omega, as you go around this, is not single valued. So think of it this way. Take the hemisphere. What we're going to do is that we're going to pick the vector field on the top as an, vector field on the bottom as as, and we cut the hemispheres open. We glue them together with a gauge transformation, non-trivial gauge transformation on the boundary. right? We construct something, a gauge transformation, or a vector field, which is all good and it's all fine. But you're dealing with gauge transformations that are non-singular value. They're multi-value. As you go around the circle, the gauge field changes by G, which is the magnetic monopole.
Omega change by value, not G, right?
Yeah, the gauge. Well, A changes by whatever is this expression. Well, A changes by AN minus AS. Right? Good. It's important that omega is all invention is in our mind, right? If we're insisting on when we knew that omega is all made up anyway, right? Omega is all made up. The only thing that's physical are the wave functions, right? The single valuedness of wave function is important. That we try to ensure by these quantization conditions. But the gauge field being singular valued is not a big deal. It's not important. Another way of saying all of this is that the gauge transformation of interest is a topologically non-trivial U1 bundle on S2. If you remember our geometric description of gauge theory, we said that this is a U1 theory. So at each point on space, there is this U1 circle, right? A choice of gauge is just like a section of this. Now, as you go around S2, we're talking, as you go around the equator of S2, this gauge transformation is topologically non-trivial, it's twisted, right? So it's a topologically non-trivial U1 bundle on S2. This is that gauge transformation that will, so A and an A cell. If you care about topology, this integer n here is called the first Chern number. Yeah.
So standard ENM would be a topology trivial number.
Yeah, the gauge transformation. Well, the choice of vector field you'd write down. The gauge vector field will be defined everywhere. It will be all just fine, right? So a single valued, therefore, it will be trivial. I mean, when it's trivial, it means that you could say it to 0, right? You could trivialize it everywhere. Good. Any questions about this?
Some scale potential.
Wait, what? Say it again.
Why do we want to like stick to that in
Well, one of them, either electric or one of them, recall what this business was, right? And when you think of this as a relativistic theory, you immediately realize that what you're dealing with is this. Hopefully I'll get this right. Yeah, that's good. You realize that if you package, oh, sorry, what was that? Yeah. If you package things like this, is that correct? That seems correct. If you package things like this, you're dealing with F, well, actually, let me draw the simpler thing. So 0, 0, 0, 0, dx, dy, dz, right? I forget. dy, dz, dx, I think there's a minus or something. Relativity told us that you have to package it this way, and all of these Carol and divergence and all of that was given to you by relativity, right? It was the elegant, when we wrote down the equations of motion, this is all that there was to it, right? So, yeah, there's not much freedom. the form of the equations are prefixed. Maybe I didn't answer your question.
I think I was just wondering, like, if we just scale up this.
I'll play around with it. Maybe we'll discover a new theory. But it is, you learn a lot. You learn a lot by playing around with this. But then if you think about it in terms of differential forms, there's really no choice. Any other questions?
Okay, so just clarification, so like Berry curvature and the Chern number of a band is just this, but in K space. So that's essentially right.
K space? What's K space?
Like in momentum space.
Oh, momentum space.
Right, like
Sorry, repeat your statement. Berry curvature is repeat your statement again.
I was just like clarifying, like this theory just carries over as is to like topological insulators and stuff. It's just that instead of B magnetic field, we just have B Berry curvature. Right, and then
So, okay, maybe I didn't understand, but Berry curvature is just regular electrodynamics without magnetic monopoles. You're dealing with Berry curvature, right? It had to do with the fact that we discussed it, right? Like you go around a charged particle above and below, and you pick up a phase. And that has to do with the curvature, the gauge field curvature.
yes, I meant like the Berry curvature in band theory.
Oh,
It's like it is just.
yeah, I do not know much about it.
Okay, I think it is just this.
It might well be, I do not know much about it. I wish I knew more condensed matter. This is always a problem with that. But I'll comment on topological insulators, actually. Sorry, my bad. Any other questions? All right, good. So, theta term in equal form. The magnetic monopole, we close that chapter, it's all good. Consider Maxwell action in equal form. This is the Maxwell action. You could view it as integral of d4 of x of e squared b squared. Where EI is this, oh, I missed the minus. Well, I messed up a whole bunch of things when I was trying to write this down. All right. Well, there's this term. You might wonder, what about F4 terms? F mu nu squared. What's the problem with that? What's the problem with that? They're irrelevant. They are less and less relevant. In principle, you should include all of them. But then renormalization group will tell you that you don't need to worry about it. But turns out, so this is a second derivative action, second order in A. What we're doing is that we're doing expansion in number of derivatives and number of fields. So higher number of fields is out of the picture, but what else can we include? Remember that in abelian gauge theory, F mu nu is gauge invariant. F mu nu A in non-abelian gauge theory was not. But in abelian theory, F mu nu is gauge invariant. Do you have a question? Okay. We defined in QFT1, I believe we did, we defined the dual gauge field, which is basically contraction of F alpha beta with this. So those of you guys who know differential forms, you know that this is just this. And it depends on the metric, but let's not worry about that. All right. What does this star operation, Hodgel star, do? Star F mu nu, if you just view it as this guy, is exactly like F mu nu, but if you recall, it sends E to B and B to minus E. This theta term that we've been discussing in various places is star of f mu nu, mu nu f mu nu. This guy is actually theta e squared over 4 pi squared integral of d of x e dot b. Good. In 4 dimensions, it's very important that theta is dimensionless. So it's just a parameter. Now, I said in various points that S theta is a topological term. A simple way of making sense of that is just noticing that this term is a total derivative. You could write it in this form. So when it's a total derivative, it means that it's only a boundary term. In the absence of a boundary, it's not there. Or said that differently, it does not change the equations of motion. That's what it means. That's what we mean by calling it topological. If you know differential forms, you know that we did to write down this term, we didn't use the metric. That's another way of saying it. But this term simply doesn't change the different equations of motion. This is f wedge f, right? There's no metric. So here I put star of f mu nu, but it's still f wedge f. Is it clear? Everything's good. How many of you guys know differential form? You do. All right. Do you know what? So f is a 1 form. F is a 2 form. You want to integrate over space-time, you need a volume form. So you need a 4 form. What is the star of f? What form is that? D minus 2. So star of f, wedge f, is always something you could integrate. That's why the Yang-Mills term always exists. But f wedge f is only for 4 dimensions. So what would it be in 2 dimensions? Just f. What would it be in 6 dimensions? Yeah. Remember the anomaly term we were calculating? In 2D, it was coming out as f, and 4D were coming out as like, yeah. So that's all of that is. And in odd dimensions, can you have such a term? No. What would be the issue? Gauge invariance. Because F is gauge invariant, a billion gauge theory is gauge invariant, but A is not. So you might be tempted to say, oh, A wedge F or something, but that's not gauge invariant. You have to build it out of F.
A wedge F is just transients.
No. Chern-Simons theorem is gauge invariant. Chern-Simons theorem is in the abelian gauge theory is A wedge F. But the full thing is A wedge F plus A wedge A times 2/3. Yeah. And this is the Chern-Simons.
I was only thinking about that.
So F wedge F is the D of the Chern-Simons Lagrange. When I say it's a total derivative, anyway, we saw that, right? Well, maybe we did. But all right, good. Is this clear? We're not discussing Chern-Simons for now. Maybe next lecture I will discuss it. Now, all right, up to here we've been assuming theta is just a constant. But what if it is a field? What if it depends on space-time? Then it would change, it would appear in the equations of motion. When you promote theta to a field, that field is called an axion. If every time you hear axion, it means that take the theta, promote that to a field. Of course, promoting it to a field also means that you will have a kinetic term for this theta term, right? But let's not worry about that for now. Let's just focus on how making theta x and t dependent will change the equations of motion. This is the connection to the topological insulators. Okay? So what happens is, well, now you have to vary this action as well. The divergence of E becomes minus E squared over 4 pi squared. By the way, you guys recall that we had a simpler way of writing this down. We defined alpha, which was E squared over 4 pi. So sometimes I use alpha over pi, right? So E squared over 4 pi squared, the what's this called? Oh my God, gradient of theta dot p. So it's if theta has spatial or time gradients, it will change the equations of motion. How? The gradient of theta acts as an electric charge density in this equation. It would also change the right-hand side of this equation. E squared over 4 pi squared theta dot b plus gradient what's it called? Outer product? No, yeah, cross E. This acts as a current density, right? And then the Bianchi identities are Bianchi. Is this point clear? So to see this a little bit better, we're gonna go through the example of topological insulators. A topological insulator is a material where inside the material, theta is equal to pi. Outside the material, theta is equal to 0. So it acts effectively as if it changes theta to pi. I'll explain in a little bit that theta is, I've been calling it an angle, which makes it sound like theta is between 0 and 2 pi. It actually is, and I'm going to prove it in a bit. But let's just go with it for now, right? So it's a material where that just inside the theta is equal to pi. So once you have a chunk of topological insulator, theta will be space-time dependent. Let's say you put this chunk of material, this is the z direction, this is the y, and this is the x direction. Time is time, right? Let's say you put it in negative z, right? And this is just vacuum. Apply a magnetic field in the z direction. There is del z of theta here. So this equation, B is in the z direction. Gradient of theta is in the z direction. This means that there will be charge density on the boundary. This is the charge density. Alpha is E squared over 4 pi, del z of theta, B over pi. You could view this as a charge density per unit area. 1 second. And that's just proportional to B. Yes?
Del z theta is not equal to 0 only at the boundaries.
Yeah, it's a direct derivative. Yeah, step function. So you end up with a charge density here, which in turn will make an electric field outside. So topological insulators are these kind of materials that if you apply magnetic field to them, they will basically outside of them, they will generate an electric field in the same direction. Think about it as E dot B, right? Once you turn on one of them, the other one will turn on the other side. Good. But now there's something more interesting, Hall conductivity. If you apply an electric field in the direction of the boundary, so this is Y, remember this is Z, and then X sticks out of the board, nothing is time dependent. So you apply E of Y. This term is not there because theta is not time dependent. This is in the Z direction. This is E of Y, so you end up with a current in the X direction. Right? What is that current in the X direction? It's alpha E of Y. That current in turn will generate a magnetic field, and that magnetic field is in the same direction as E. So you could define a Hall conductivity for this object, and E squared over half E squared over 2 pi H bar. So topological insulator, this is related to quantum Hall effect in case you guys know about that. Topological insulator has Hall conductivity half. This is all I was gonna say about topological insulator, right? So theta term being space-time dependent will have important consequences, right? In particular, it will have local dynamical consequences. Theta, which is a constant, is topological, right? It will not, a topological theta, constant theta is topological, it will not have a classical consequences, but it will have quantum consequences. Or, yeah. Good. We'll see that in the next lecture. That's not this lecture. For the same reason that the magnetic background gauge field, right? Constant gauge field might not have any it does not change the equations of motion. However, quantum mechanically, things might change because of Wilson. But there's a simple way of arguing for all of this stuff. In the remaining time, I just want to argue, why is theta periodic? Why am I calling this parameter theta angle? Now, it's very important that, let me just say this right away. Classically speaking, theta is just a constant, which is any constant. So theta becoming an angle has to do with quantum mechanics, otherwise known as quantization conditions. There's a way of arguing for it from Dirac quantization stuff, but I'm going to do it a little bit differently, and then it's up to you guys to see the connection between the two. The point is the following. S theta, the theta term, the contribution of the theta term, is H bar, we'll show that in a second, theta times n, where n is an integer. Now, something important happens here. S theta has only one time derivative. You guys see why? Think about that. It only has a one time derivative. Which means that in Lorentzian action, when you have IS, right? Both in Lorentzian action, what you have is e to the power of IS diagonals plus S theta, right? This guy is real, everything is fine. But when you construct the Euclidean action, right? Here, what happens is that every t goes to I tau. This guy will give you a sign in the kinetic term, right? This guy will pick up an I. So the contribution of the theta term to a partition function is a phase. Now you should already see that you're going to end up with quantization conditions, right? So it contributes to the partition function as e to the power of I s theta over h bar, e to the power of I n theta, therefore theta is periodic. Now I'm going to argue this in a little bit more detail, or just a little bit more detail. Consider U1 gauge. So we're going to sit in the Euclidean theory. Okay. The simplest example is four-dimensional torus, because I'm talking four-dimensional theories, right? And it's a Euclidean theory, so S1 times S1 times S1 times S1, right? And all of these S1s, I take them to have a radius R for their S1, right? So 2 by R, you go around 2 by R, you're back. So let's see what happens. Let's focus on just one S1. And for simplicity, I'm going to take the electric and magnetic field to be just E and B, where E and B are constant. You could make this, you could repeat this argument, make these guys dependent on space, time, and everything will go the same. All right. S theta is an integral over space time, Euclidean time of EB. It's constant, right? But this is on T4, so that's what we're gonna look at. Let's first imagine, oh, sorry, whoops. This is the circle in the x2 direction. I wrote it S2. This is a circle in the x2 direction. Consider A2 as the zero mode of A2 of x2 as a zero mode here. Do you know what zero mode means on a circle? It means integral over of dx2, A2x2. Right? You integrate it over the whole circle, that's a zero mode. It's independent of x2. Under gauge transformation, A2 goes to A2 plus del 2 omega. But choose this large gauge transformation. This is non-single value. Right? We said that we're gonna assume that under these large gauge transformations are also redundancies, right? If A2 is to be single valued, it means that it has to be periodic by this periodicity. Magnetic field is del 1 A2 minus del 2 A1. So let's pick a choice. A1 is 0, B is del 1 of x2. So constant B means that A2 is Bx1. Oops. Oh. My bad. Oh, my bad. Sorry. Yeah, my bad. Sorry. I think I should pick the direction. I should pick the direction to be x1. So this is x1. I apologize. I think here I had it correct, but it has to be, I had to pick x1 direction.
But then how will the A2 thing be changed? Is there?
Yeah, I think it's A1. This is all A1. Did I mess up? Wait a second. All right. Let me run this argument. Next time when I review it, I'll make sure that everything is fine. I think this is x1, this is A1. But okay, I'm not quite remembering how it works. So the point here is that all of these A1s, A2, A3, and A4, they're all around S1s, and they have to be all periodic this way. Now, if you want a constant field that's only consistent with, oh my God, I think I really messed this up. Yeah, I'm not remembering. The fact that a constant field means that a constant B means that A2 is like this. That's only consistent with periodicity condition if B is quantized this way. Okay, I did a really poor job by messing up the A1 and A2. I apologize. Well, next time when I go through it, but let's accept this for a second. And then next time I'll repeat this, review this again. So H bar, the requirement that there is gauge invariance under large gauge transformations, that as you go around the S1, it doesn't come back for the gauge. The transformation not single valued, forces you to have the magnetic field to be quantized in units of H bar or 2 pi E R squared. If you integrate this B over dx1, dx2, a torus, you get 2 pi H bar N over E. This is some sort of Dirac quantization. Similarly, you could run the same argument for E as A3 and del 0 of A0. You pick a similar gauge. I think this time I didn't mess up the indices, but anyway, you repeat it and you find the condition that the electric field also has to be quantized this way. This is the integral. Putting all of this together, E dot B, D4 of XT4, because E and B are just constants and they're both in the Z direction, for example. It just gives you 4 pi squared H squared over E squared N, where N is Nn prime. So it's still an integer. This is S theta. It appears with an I next to it in the exponent. So theta must be an angle. I messed up this. So sorry about that. But I'll repeat this argument next time. Okay, so yeah.
We did all of this when you assume that theta is constant, right? That
Yes. Yes.
so when it's not a constant but a function, space time varying function, then would the things change? Can you still calculate it as an angle?
So yeah, the thing is, when you promote this to a field, it would be a S1 field. Like it would be a S1 valued field. It would be an angle valued field. It would be like a U1, right? It would take its value from 0 to 2 pi. That's sort of required for all the consistency conditions. So now, if you promote this to a field, like for example, take it to be an axion, your analysis was way more complicated, but still the same argument holds. So it's an angle valued field. All right, in summary, what did we discuss today? We started our discussion of gauge theories, some non-perturbative aspects of gauge theories. We talked about Dirac quantization conditions. These were conditions where we first said that we introduced magnetic monopoles in electromagnetism in 4 dimensions, right? And it told us about the Dirac quantization condition, which would relate the magnetic and electric charge of all the particles in the theory, right? This story of rotating one of these guys and in the presence of another one holds for any pair of particles. For generic dion of electric charge E and magnetic charge G, as you put one of them E1, G1 here, and then take E2, G2 around it, you end up with this condition. E2, G1 has to be 2 pi N and Z. This was the condition, right?
We did an edge bar, maybe. And the next one.
By the way, you know where the origin of this H bar is? There's a question. In the notation I've been using all throughout this course, there shouldn't be an H bar there, right? You eat the H bar in the coupling, right? I was writing e to the power of my action, my path integrals, for e to the power of is, not s over H bar. These are gauge theories, right? So, yeah. Is that clear what I'm saying? these are gauge theories, so I normalize everything this way. Right, so I'm eating H bar inside G squared. Right, so here I have EG, so it's like E squared. We talked about how the requirement of insisting on getting a local action for electromagnetism with magnetic and electric charges force us to take these gauge configurations that involved large gauge transformations. These are non-single valued as we go around. Like for example, we had to take to talk about the vector potential around the vector potential that describes the magnetic monopole. We had to talk about gauge transformations that were non-trivial U1 bundle on S2. We talked about theta term very briefly. We said that it's a total derivative. That's the sense in which it's topological. It doesn't change the equations of motion. If you promote theta to a field, it will the delta of theta, the gradient of theta. If let's say theta is time independent, it only depends on space, like as in topological insulator. The gradient of theta will act effectively as charge density once it's aligned with when you dot it with B. The element of the gradient of theta that's in parallel to B will act like charge density. The element of the gradient of theta that is cross gradient of theta cross E will act like current density, right? In the case of topological insulator, we said that this material acts as if theta is equal to pi inside it. So if you apply an electric current perpendicular to its boundary, right, on the other side, there will be magnetic field produced that is in the direction of its magnetic field. Electric field will produce in the direction of its magnetic field. If you apply B and E on the other side, and if you apply electric field in the direction of the boundary, outside of it, it will produce magnetic field in the direction of boundary. It's just a consequence of these extra terms that have to do with gradient of theta. And finally, I tried to explain why theta is an angle, meaning that it takes value between 0 and 2 pi, but I failed miserably. I'll repeat that argument again, but yeah. All right, any last questions? Sorry, I went over time.
And the topological insulator discussion.
Yes.
Where he said that the theta is equal to 0,